And welcome to Space Oddities. Thank you for joining us this afternoon on what could well prove to be a rather historic day. Anyway, I'm Andy. I'm here with Michael and Daz. Hi guys, how are you doing today?
Hi there. Hi Andy. Yeah, we're all fine. Thank you very much.
Good.
Wondering what all this is all about?
Well, we've got two major scientific announcements this afternoon. The first one is from a project called NANOGrav, which has been running for 15 years, and they've been studying pulsars. In fact, they've been studying 68 pulsars off in the universe, and they're studying their signals because, as you may know, there's a class of pulsar called a millisecond pulsar, and these rotate incredibly quickly. The fastest one so far rotates 746 times a second. And they are the universe's most accurate clocks because this rotation period is incredibly accurate, and we can measure them incredibly accurately. Now, the idea behind this is that off in the universe, somewhere a long time ago, you had two galaxies merging, and their respective supermassive black holes came together after a long time, maybe millions of years, into a giant supermassive black hole. And that merger produced very, very low frequency gravitational waves. These gravitational waves are still traveling across the universe because, according to Einstein's predictions, gravitational waves never die out altogether. They get fainter and fainter, but they never die out altogether. Oh, we suspect there are quantum effects that will eventually kill them, but Einstein didn't know about those. But the baseline of this is, if the light or the radio signal or the X-ray signal or whatever it is from the pulsar hits one of these gravitational waves, it's delayed in its transmission across space. So the wave arrives on the Earth ever so slightly late, meaning that it's encountered a gravitational wave on its journey. Now, these are exceptionally low frequency gravitational waves. They have a very, very long wavelength. It's said that some of these gravitational waves, one wave may pass through the Earth each year, so they have an incredibly long wavelength. But if one of those waves arrives later than expected, or one of these pulsar signals arrives later than expected, it was thought that this could be due to the presence of a gravitational wave, because space with a gravitational wave is stretched and squeezed, which means that the photons from the pulsar have a slightly longer journey to make, and they arrive slightly later. And this is what the announcement today is all about. Now, actually, the NANOGrav project, they've scooped themselves because they actually released the scientific papers yesterday. So we do know what this announcement is about, but I'm not going to tell you, viewers, because I want you to hear it live as an announcement from the horse's mouth, as it were. So let's go and see what you two guys think. What do you think about all this? Possibly a very, very historic day.
Well, the thing is, I'm really big into the gravitational waves, and I think it's not just the fact that we've discovered gravitational waves; it's the ingenuity that's gone into actually catching them, and it's the observatories that, if you can call them that are actually catching these things. They're huge machines. We've got plans for even bigger and better. But it's absolutely fantastic. So I'm really intrigued to see what they've actually got to say today. As you, Andy, before COVID, we used to have the little app which was Chirp.
Yes.
And we'd be eagerly waiting wherever we were for it to go off, and then we'll be straight on there, because they used what do they call it? Multiple systems to find these things. What it would do, it would be detected once they've had a quick look at it, rather than wait to confirm whether it is a merger or something. It could be even something terrestrial or something like that. Then they can, that they will then contact as many observatories as they can, and they will all swing their telescopes in that direction to see if they can actually catch what this event possibly could be. But over the years, the detectors have been detecting the waves, but they haven't been very directional because they haven't been that sensitive. And so it's always been sort of like potluck whether or not they actually picked anything up.
There's only been one gravitational wave event where they found an optical counterpart, and that was GW 17817, which was the collision of two neutron stars in 2017. And that was tracked down to the galaxy NGC 4993, a few billion light years away, and you can very clearly see in the photo of the galaxy this explosion in one of its spiral arms. So this was the first time that we got to know about these events from gravitational waves first, and then finding the actual event with optical telescopes later.
Yeah.
So what do you think, Michael? Excited?
It's very, very deep, isn't it?
Yeah, yeah, yeah. But you should be happy, Michael. I mean, we should all be, because this is the very beginnings of a totally new science. We're right in at the beginning of a new science. So that's why it's so exciting, because gravitational wave astronomy, the first detection was only reported in 2015, so it's only 8 years old as a science. And already, well, I won't say what we're detecting, but we will get onto that in due course. But it is quite a momentous announcement. Now, viewers, after this announcement, you will see on our channel there's another live stream, because in an hour's time, there's another major announcement today from the IceCube Neutrino Observatory about some neutrino detections they've made. And this, again, must be something pretty big, because last year they announced that they'd captured a neutrino from another galaxy, which was pretty wild. So whatever it is today, it must be wilder than that. And unlike the gravitational wave thing, we don't know what the hell they're going to announce. So do join us in an hour's time as well, also on our channel, for the announcement from the IceCube team. IceCube is a neutrino detector at the South Pole, buried in, I think it's actually a square kilometre of ice, isn't it? I think, if I remember rightly. But
yeah, something along that line.
Neutrino detector that's been detecting neutrinos, not coming just from space, but coming through the Earth itself as well, because neutrinos can pass through anything without noticing it very much. So,
yeah, it's a cubic kilometre.
Cubic of neutrino detectors buried in the ice at the South Pole. So we're going to learn all about that in an hour's time. What
they should have called it the cubic kilometre, right?
Yeah. No, they should have called it the square kilometre away. Oh, sorry, that's already been done.
Yeah, somebody's already got that.
That's another amazing telescope that's coming online by the end of the decade. Anyway, we'll talk about that some other time. So lovely to see people today. How are you all out there in YouTube land? And Astronebula's here, and Jack's here. So Jack has got a question for you, Daz.
Yeah, I did see that. Where would I recommend he go in Shrewsbury? I would recommend. I mean, I don't know whether he's. I don't live in Shrewsbury. I'm outside, so. I would recommend, if you've got time, to definitely do the castle, because it's got the military museum in there, which is well worth a look. But I'll have to think about that one, because living here, of course, it's and if it's a nice day, go down the Dingle, which is in the quarry, as they call it, the quarry, which is a big open grass area in the centre. And you've got the Dingle, which was planned and built by a chap called Percy Thrower. Can you remember Percy Thrower?
Percy Thrower.
Yeah, Percy Thrower. So yeah, there's several places. I'll drop some in the chat later when I've had a bit of a think, because I'm guessing you'll be in the centre of town. But I'll sort something out for you, Jack. So don't worry. Anyway, back to the science.
It was like the thinking man's Alan Titchmarsh, wasn't he?
Yeah. Well, the thing is, he lived in Shrewsbury, and although he was old, he died prematurely because he, unfortunately, somehow he managed to shoot himself, if I remember rightly. And unless I'm thinking of somebody else, but yeah, if you go down to the quarry, as you go in through the main gates, on the right hand side, there's his house, which is now the Royal Horticultural Society's centre. Oh, excuse me. And it's, like I said, and if you go to the left, just follow it around. The dingle's actually sat down inside a small quarry itself. So, but it's got some lovely flowers there. There's a big pond there, some big fish. But just to sit down there in all the colours and the glory and just people watch is absolutely fantastic.
Right. Okay.
So, yeah.
Right. Well, I'm just looking at this business of Percy Thrower. And you must have been thinking of something else, Daz, because he actually died of Hodgkin's lymphoma. So
Oh, okay then.
Perhaps you were thinking of Kurt Cobain.
No, not quite. I don't think Percy Thrower was hard rock.
Well, you don't know what he got up to in his spare time.
Well, yeah, if he's working in the quarry, he was getting down with the hard rock.
Of course, says, how could we forget he designed the Blue Peter Garden?
Ah.
Oh, yeah, of course he did. Yeah,
he did. I was watching an episode of Blue Peter from 1974 yesterday.
Oh.
Because I obviously had nothing better to do. But yeah, it's quite amazing how things were different then. Society was so different. There we are. Right, okay. So, a message from Rachel. Isaac recognises those noises. Oh, there we are then. Those voices, she says.
Oh.
So,
okay then.
There we are. Okay, well, we're getting close. Checking the stream. Right, okay, with no sign of any movement yet on the stream from NANOGrav. So it's actually it's being hosted by the National Science Foundation. This video, as you may know, big American organization that funds American science. So we're just waiting to see what happens. As always, viewers, if you have any questions at all, please put them in the comments. We'll do our very best to answer them. But this really is the culmination of a 15-year project by NANOGrav to study the signals from these pulsars, 68 of them in all. And of course, if you look at them on a map, they all look very close to the Earth, but of course they're not. They were all of them many light years away. So if they have discovered something about the presence of gravitational waves and those pulsars in those pulsar signals, it'll be quite a remarkable step forward for the new science of gravitational wave astronomy. NANOGrav have the ultimate goal of detecting gravitational wave signals from the Big Bang itself, because although light could not travel the universe until 380,000 years after the Big Bang, gravitational waves had no such restriction because they are ripples in the fabric of space itself. So it should be possible one day with equipment that we don't have at the moment. We don't have the technology. Well, I think we have the technology, but we don't have the observatories in place yet to detect these extremely long wave gravitational waves from the actual Big Bang itself, which if we manage to do that, maybe, who knows, the only real way we're ever going to have of studying the Big Bang in detail. So, excuse me one moment.
Well, of course, this the gravitational wave detection was one of Einstein's mistakes. He thought we would never actually be able to have the technology to detect them.
Well, he did.
Although he predicted them.
Yes. Well, he predicted them, and then he didn't believe his own predictions. And for 20 years, he hummed and hawed about whether they actually existed. 20 years, he couldn't quite bring himself to believe that gravitational waves could be a real thing. And then eventually, he convinced himself they did exist, but then said that they were so very, very weak that humans would never have the technology to detect them, which, of course, as we now know, he was wrong about. It's one of the only instances you can think of when Einstein was actually wrong about something. So so it's going to be really interesting to see. I find myself wondering what Einstein would have thought of the field of gravitational wave astronomy. He wouldn't have believed it. He really would not have.
No.
that.
Anyway, I'll be back in a minute, guys. Okay.
Okay, Michael.
Yeah.
He wouldn't have believed that humans could have come this far with what we've achieved, the gravitational waves, and when you think these waves are so incredibly weak that they stretch space-time by about 1/10,000th the diameter of a proton. This is the same as detecting a change in distance. Oh, right. I think we're going live now.
Okay.
Research team. Before we begin, a few housekeeping rules. This event is on the record and being live streamed on YouTube. If members of the media would like to request a more in-depth one-on-one interview with any of the members of the research team, please contact media@nsf.gov and they will coordinate details. My name is Michael Cabanero. I'm the director of the Physics Frontier Center program here at the National Science Foundation. We're here today to mark the occasion of the publication of new results from the North American Nanohertz Observatory for Gravitational Waves, familiarly NANOGrav. We're also here to describe those details and to discuss the significance of the new results. Of course, we're also here just to celebrate a remarkable scientific achievement that's been 15 years in the making. To help us celebrate this result, we're joined by a number of distinguished guests. Dame Jocelyn Bell Burnell, discoverer of the first radio pulsars, chancellor of the University of Dundee, joins us remotely. Kip Thorne, Emeritus Richard P. Feynman Professor of Theoretical Physics at Caltech, a Nobel laureate and world-leading expert in the study of black holes and gravitational radiation, has joined us here at NSF headquarters. We are also pleased to welcome Dr. Jim Jackson, Director of the Green Bank Observatory, Dr. Tony Beasley, Director of the National Radio Astronomy Observatory, and Dr. Adam Cohen, Director of Associated Universities, Inc. We had also hoped that Olga Figueroa Miranda, Director of the Arecibo Observatory, would join us today, but I think she had some problems with her flight and wasn't able to make it. Last, but certainly not least, we welcome Dr. Javier Siemens, Principal Investigator and Co-Director of the NANOGrav Physics Frontier Center. And he's brought along with him a significant fraction of the NANOGrav collaboration. I think a rather boisterous faction of the collaboration also. Now for a brief introduction to the panelists who are representing the collaboration here today. From left to right on the stage, Dr. Stephen Taylor, Chair of the NANOGrav collaboration, co-lead of the 15-year gravitational wave background paper, and an assistant professor at Vanderbilt University. Dr. Thankful Cromarty, Chair of the Timing Working Group, co-author of the 15-year timing paper, and Einstein postdoctoral fellow from Cornell University. Dr. Michael Lamb, co-chair of the Noise Budget Working Group, co-author of the 15-year detector paper, and a research scientist at the SETI Institute. Dr. Luke Kelly, chair of the Astrophysics Working Group, lead of the 15-year astrophysics paper, and an assistant adjunct professor at the University of California, Berkeley. Welcome, panelists. Oh, I forgot one. Sorry about that.
I wonder why the actual picture is
Finally,
small in the corner.
Dr. Maura McLaughlin, co-director of the NANOGrav Physics Frontiers Center, a steering committee member of the International Pulsar Timing Array, and the Eberly Distinguished Professor of Physics and Astronomy, West Virginia University. I saved the best for last, so it's okay. Okay. And now I'm pleased to introduce Dr. Sean Jones, Assistant Director for the Directorate of Mathematical and Physical Sciences. Sean?
Great. Thank you, Mike. And I'm loving the energy that's here in the room. Good afternoon, everyone, and welcome. In 1995, the Hubble Space Telescope revealed the Hubble Deep Field, a tiny sliver of the night sky brimming with a veritable zoo of galaxies in various stages of evolution. In 2022, the James Webb Space Telescope refined and deepened that image, fantastically displaying galaxies more than 13 billion light years away from Earth. Aided by the state-of-the-art optical and infrared telescopes and decades of advancement in instrumentation and data processing, we perceive a static image of distant galaxies. Today's announcement shatters that perception of a static universe through the direct observation of gigantic gravitational waves washing across our Milky Way galaxy, spawned by cataclysmic events, including some from the most distant regions of the cosmos. These observations reveal a rolling, noisy universe alive with the cosmic symphony of gravitational waves.
Ah, that's why.
Or here.
Supermassive black holes lurk in the hearts of most galaxies, and galaxies grow by merging with other galaxies. When that happens, their black holes also merge and grow, becoming more and more massive over time. How exactly this happens is not fully understood, but the universe is telling us its secrets in gravitational whispers. We just have to listen. Just as sound waves are vibrations of air molecules, gravitational waves are vibrations in the fabric of space-time. When two massive black holes spiral toward each other, they produce gravitational waves that travel through the cosmos at the speed of light. If we imagine the universe as a grand symphony, these merging supermassive black holes are the bass players. As they orbit each other, these black holes play the deep bass notes that echo throughout the cosmic concert hall. But that's not all there is to the symphony. In the background is a faint but pervasive hum produced by the collective motion of massive objects throughout the universe, from the earliest moments of the Big Bang until now. This gravitational wave background is truly a harmony of space and time. NANOGrav is an NSF-funded collaboration of astronomers and astrophysicists. Our goal is to solve some of the deepest mysteries of the universe by studying the gravitational waves produced by these dancing monster black holes. These waves are light years long and can only be detected by the most extraordinary instruments. To measure these giant but subtle ripples in space-time, NANOGrav created a galaxy-sized detector using some of the most incredible objects in the cosmos, rapidly rotating neutron stars known as millisecond pulsars. Pulsars are the ultra-dense remnants left behind when massive stars reach the end of their lives and explode as supernovae. These pulsars are also cosmic beacons. They spin extraordinarily rapidly and with startling regularity, releasing pulses of radio waves with each rotation. Astronomers detect those pulses using giant radio telescopes. By monitoring the radio pulses from these ultra-precise cosmic clocks, NANOGrav can detect the slightest deviations in the regularity of their timekeeping, and these deviations trace ripples in space-time. This galactic scale detector is called a pulsar timing array. NANOGrav has now observed an array of dozens of pulsars for more than 15 years, and the results are astounding. We are finally hearing the faint background hum likely coming from in-spiraling pairs of supermassive black holes. With time, astronomers expect to pick out the individual instruments in this cosmic symphony, revealing unique insights into the evolution of galaxies and the history of the cosmos.
Well, there we are. That is amazing.
Excellent, excellent. Truly, truly amazing. Yeah, and great speaker as well. Yeah, and narrator. Truly, truly amazing. This achievement was made possible by an extraordinary collaboration involving more than 190 scientists from 70 institutions, the North American Nanohertz Observatory for Gravitational Waves, and NSF Physics Frontier Center. This project is a shining example of the transformative advances possible through long-term investment in NSF facilities and researchers and students at institutions ranging from small colleges to extremely large universities all across this great country. The National Science Foundation is proud to support daring team efforts like NANOGrav to expand our knowledge for the benefit of society. With us today are 5 members of the NANOGrav team who will describe their recent published results. We'll start with the chair of the NANOGrav collaboration, Dr. Stephen Taylor. Dr. Taylor?
Thank you, Sean. Distinguished colleagues, honored guests, and for all those following along at home, it's a pleasure and relief to finally share the following news with you. Over the last 15 years, we, the NANOGrav collaboration, have been on an audacious mission to find the low-pitch hum of gravitational waves coming from all over the universe, washing through our galaxy to stretch and squeeze space-time between the stars. Well, now we're here today to finally tell you all that patience is a virtue. Friends, our hard work has paid off, and we're really doing it. Even more excitingly, this is all the culmination of a coordinated process with our international colleagues using telescopes in Europe, India, Australia, and China. In the following, I'd like to tell you 3 things. First, about our detector, then about how gravitational waves imprint signals in our detector, and finally, how we found evidence for gravitational waves. First of all, we didn't do any of this just by building an instrument on Earth or even in the solar system. In fact, we harnessed a collection of astronomical objects in our neighborhood of the Milky Way to act as one big gravitational wave antenna. These objects are pulsars, and they're about as close as we can get to clocks in space. Pulsars are these super dense remnants of stars that have exhausted their fuel and contracted inwards, squeezing about the mass of the sun into the size of a city. And if you set that object spinning hundreds of times a second, blasting out beams of radio waves, you've got yourself a pulsar. Now, those radio beams I mentioned wash across Earth every time the pulsar spins around, and we measure this as regular pulses in our radio telescopes. In a way, these pulses are like the ticking of a clock out in space. And this makes pulsars perfect to study phenomena associated with Einstein's relativity theories. And while these pulsars are extraordinary objects in their own right, to us, they are the components of our vast galaxy-wide gravitational wave antenna. This is galaxy-scale hacking. Now, when gravitational waves cascade through the galaxy, they warp space-time between the pulsars, causing the ticking of these cosmic clocks to change in a predictable and correlated way among the numerous pulsars that we monitor. Without gravitational waves, the ticking rate of these pulsars should be completely independent, with 0 correlation. Remember, these pulsars are separated by hundreds to thousands of light years, after all. But with gravitational waves warping space-time in the galaxy, and with Earth as the common endpoint of all of our pulsar observations, Einstein's theory of general relativity predicts a unique pattern for the correlation in those ticking rate changes between pulsars spread across the sky. Here is that pattern. This is the unique fingerprint of a background of gravitational waves, and there's nothing else we know of in the pulsars, in the intervening gas, or on Earth that can produce this pattern. Now, with almost 70 pulsars used in our gravitational wave search, this gave over 2,000 ways of pairing up the pulsars in a correlation analysis. For each pair, separated on the sky by a known angle, we measured the correlation of how much the ticking rate of their pulses are changing and offset from modeled behavior. And in what I show you next, we've distilled all that information into some average correlation measurements in 15 points between 0 and 180 degrees of pulsar sky angle separation. This makes it a ton easier to visualize, even though our detailed analyses don't require this. You know, I think I've dragged this out long enough, but that gives you a taste of what it's like to wait 15 years, okay? Here is what NANOGrav sees.
Oh, wow.
Gorgeous. This pattern, imprinted in data from vastly separated pulsars across the galaxy, shows incredible agreement with the fingerprint of gravitational waves described by general relativity. A lot of information is hidden when we visualize our data this way, but our detection statistics show the chances of nature delivering these results without gravitational waves being present is less than 1 in 1,000, and in some of our tests, 1 in 10,000. That would be like trying to flip a coin and get heads 10 times in a row to 14 times in a row. And this significance will march higher in the future.
Wow.
NANOGrav is a gravitational wave detector and collaboration of people that intersects many different disciplines. My colleagues are next going to describe how we go from observing pulsars to modeling noise, finding evidence for gravitational waves, and ultimately constraining the astrophysics of supermassive black holes and theories of the early universe. It's my pleasure to hand over now to Dr. Thankful Cromarty to describe NANOGrav's pulsar timing campaign. Thank you.
So what do you think, viewers? Any reactions so far?
Thank you so much, Steve.
Well, that graph he showed was spot
as Steve
on,
just
wasn't it?
mentioned, our detector isn't something that you could build in a lab or even launch into space. It's closer to the size of the galaxy, and it's made up of dozens of rapidly rotating neutron stars called millisecond pulsars. These objects are second only to black holes in density. They spin faster than your kitchen blender.
Okay,
and they
what I was going to say was, if you look at the error bars on those points on the graph, if you sort of adjust it for the error bars, I mean that's almost a perfect fit. So
Exactly, yeah.
That's almost,
exactly. That was fantastic.
That's obviously a perfect fit. That's exactly what they're seeing. I have no doubt about that. What do you think, Michael?
Thank you so much for joining.
Can't hear you. Is your mic off?
Regular intervals that scientists
Sorry about that.
It's okay.
the signal might be coming from aliens.
Yeah, it's definitely exciting news.
Pulsars are unfathomably interesting.
It's really exciting that it looks as if this is the signature of merging supermassive black holes throughout the history of the universe, back to the first time galaxies collided.
These timing models take into account
it's amazing, absolutely amazing. Anyway, let's put the volume back up.
Arrive at the Earth. From movement of solar system bodies to binary orbital motion, and even to the interstellar medium, which is the medium inhabiting the space between us and our pulsars. For gravitational wave experiments like NANOGrav, the precision of our pulsar timing has to be better than a microsecond. For some of our sources, we know when each pulse will arrive to a precision that rivals atomic clocks. Pulsars can be studied at a wide range of wavelengths, stretching from the least powerful radio waves, which are around the same frequency as your FM radio, to extremely high energy gamma rays. But their emission is strongest at low frequencies, and so we traditionally study them using radio telescopes. NANOGrav's been lucky enough to use some of the world's largest and most cutting-edge radio telescope facilities. These include the 100-meter Green Bank Telescope in West Virginia, the 300-meter Arecibo Telescope in Puerto Rico, and the 25-meter dishes of the Very Large Array in New Mexico. So what's this detector actually made of, and what do our timing data even look like? The more pulsars scattered across the galaxy that we can time, the more sensitive to gravitational wave signals we become. And for that reason, NANOGrav's been feverishly adding pulsars to the array ever since the very beginning. Now let's take a look at the history of NANOGrav's data set. Our first data set, which we refer to as the 5-year, included approximately 5 years of data for 17 millisecond pulsars, timed using the Green Bank and Arecibo radio telescopes. The 9-year data set had 37. The 11-year data set had 45 pulsars. And the 12.5-year data set had 47. Now today, we're sharing with you the NANOGrav 15-year data set, which includes more than 15 years of timing for 68 millisecond pulsars. For the first time, we're also including data from the Very Large Array in our release. These data, as well as the brand new pipeline we've been working hard on, are available publicly starting today. Now, there's an enormous amount of science that we just sort of get for free from timing dozens of pulsars over a decade and a half with the world's best radio telescopes. With this much high-quality data, we've been able to do large-scale studies of our pulsars as astrophysical objects in their own right, instead of mere tools for gravitational wave detection. We can learn about their astrometry, which is a pulsar's motion through the Milky Way, probe the structure of the interstellar medium between the Earth and each pulsar, And for our pulsars that are in orbit with another star, we can sometimes measure the pulsar's mass and the mass of its companion using general relativistic effects. This last point is notable because precisely measuring pulsar masses helps us understand the fundamental nature of the extremely dense matter deep inside the cores of neutron stars. Now, I'll spare you from me droning on about how cool this is, but the takeaway is basically that once again, our astrophysical clocks can help us conduct science that just can't be done in an Earth-based lab. So the data in this release is the culmination of countless hours of work by NANOGrav members at all levels, including many students. Without the team's collective ingenuity and dedication, creating such a massive data set wouldn't have been possible. So with that, it's my absolute pleasure to introduce my colleague, Dr. Michael Lamb, who's going to talk to you in more depth about our detector.
Thanks to the hard work of so many people, we built our galaxy-sized gravitational wave antenna using almost 70 millisecond pulsars spread across the Milky Way, along with radio telescopes here on the Earth, and using well-tested techniques improved upon for decades. But even so, how do we know our detector is good enough to find the incredibly tiny signals produced by gravitational waves? Millisecond pulsars are the best astrophysical clocks we have, but they aren't perfect. At a very small level, they will wobble as they rotate, causing the ticks of our clock to arrive slightly early or a little late over time. Then, the pulses are delayed and distorted as they travel through thousands of light years of gas in the Milky Way. And finally, while we make the best measurements we can here on the Earth, an example of simulated data for one pulsar shown here, these aren't perfect either, so we have to properly calibrate our data and clean out radio interference in our measurements. To make matters more difficult, each Earth-to-pulsar arm of our detector is unique. And unlike most detectors we build here on the Earth, we can't go to the pulsars to measure or tweak them. Our goal has been to extract the tiny signal from gravitational waves from many different sources of noise in our detector that mask that signal. It's a really challenging problem, as gravitational waves are constantly passing through our detector, and we can't turn the signal off in order to determine how our detector behaves on its own due to only noise. Many of these noise effects can be much stronger than the gravitational wave signal we're investigating, hundreds or even thousands of times stronger. Some of these effects change depending on the radio frequencies we observe at, whereas gravitational waves are the same strength regardless. So that's one of the many ways we can pull the signal out from the noise. We needed to measure precisely when pulses arrived at our telescopes to within 100 nanoseconds or better to be sensitive to gravitational waves. Over many years, we have performed many careful analyses to uncover the sources of noise and learn how the characteristics of our signal differ from the noise sources. The statistically common signal we extract from all of our pulsars has an astronomically small chance to be produced from the individual pulsars alone. As with our previous data set, we have enormous evidence for a signal with common statistical properties. In each pulsar, the signal of a gravitational wave background may appear as a random oscillation over long timescales, but it imprints a unique pattern between pulsars that we can extract from noise. One of the benefits of our technique relies on the fact that our gravitational wave signal has a very special correlation when you analyze the data from different pulsars together. When the correlation between two pulsars is positive, that means the radio pulses are arriving either both early or both late. When the correlation is negative, then the radio pulses will arrive early in one and late in the other. Notice how Einstein's theory of general relativity predicts that the correlation in the time of arrival offsets starts positive when the pulsars are close to each other on the sky, becomes negative, close to 90-degree separation, then goes positive again when the pulsars are on opposite sides of the sky. Analyzing our 15-year data set, we find strong evidence of this correlation pattern. Something like a 1 in 1,000 to 1 in 10,000 chance that the correlations would have been produced only from noise, depending on the analyses we perform. We find that these gravitational waves have an incredibly small strength, so small that they cause space-time to change by 1 part in a quadrillion. Next, Dr. Lou Kelly will talk about what sources will cause gravitational waves of these low frequencies and these tiny amplitudes.
Thank you so much, Michael. And as Michael pointed out, the amplitude of these signals is 1 part in a quadrillion. That's 1 part in 1,000,000 billion. This corresponds to a measurement precision of about 100 nanoseconds over the course of our 15 years of data. And now, while this has been an incredibly challenging signal to detect, it's actually booming loud in terms of gravitational waves. But because we're in the early days of measuring this signal, we can't yet confirm what sources are producing the gravitational waves. We believe, however, that they're produced by some of the most rare and most energetic objects in the universe, binary systems of 2 supermassive black holes, also the coolest objects in the universe. We know that these gigantic black holes lie at the centers of large galaxies distributed throughout the universe. While the black holes themselves are only as large in size as a solar system, they have masses as high as billions of suns. Now, as galaxies grow over cosmic time, they merge with other galaxies, and this provides the opportunity for 2 supermassive black holes to come together. For decades, astrophysicists have theorized that binary supermassive black hole systems could then form and produce exactly the types of gravitational wave signals that we're seeing. Despite years of searches using traditional telescopes, no supermassive black hole binary has been fully confirmed, although a handful of very compelling sources have been identified. The signal we're measuring wouldn't be produced by a single black hole binary, but instead by large numbers of supermassive black hole binaries all across the universe. Each of those binaries produces a slightly different frequency or different tone of gravitational waves, which together produce a symphony or a hum that we call a background. Using new theoretical models, we have simulated billions of supermassive black hole binaries, predicted the gravitational waves that they would produce, and compared that to the signals that we're measuring. I want to share with you those results. Here, the vertical axis shows the amplitude of the signal, corresponding to how many binaries are out there and how massive they are. The horizontal axis corresponds to the distribution of gravitational wave frequencies, how many binaries are emitting at different tones. Models appearing towards the right correspond to binaries evolving in isolation, while models showing up towards the left correspond to binaries that are interacting strongly with their host galaxies. Here in orange is the classic, simplified model of binaries that expects gravitational wave signals to show very little interactions, binaries evolving in isolation. In blue are new, more comprehensive models of binaries, starting when galaxies merge and evolving all the way down to the small separations at which those black holes can produce detectable gravitational waves. These models include interactions with the gas and stars and the nuclei of each of their host galaxies and produce much broader expectations. Finally, this is what we measure from the NANOGrav 15-year data. And if we zoom in, we can see that the data is consistent with both models. However, there is more overlap with the blue interacting simulations, hinting that perhaps binaries may not be evolving in isolation, and even in the strongly gravitational wave emitting regime are interacting. In either case, the signal that we're measuring is a bit louder than we expected, which means that supermassive black holes would need to form binaries relatively frequently and/or with quite high masses. We cannot yet confirm whether or not supermassive black hole binaries are producing the gravitational wave background. But if it is produced by binaries, then these models offer tantalizing hints about their properties. We'll need to keep taking data, continue to develop new models and methods to find out more. Other kinds of sources have also been proposed as the origin of the gravitational wave background. NANOGrav scientists who study the fundamental properties of the universe have shown that our measurements could also be consistent with signs of cosmic inflation, the rapid expansion of the universe soon after the Big Bang. They may even be signs of new, as yet undiscovered, fundamental physics. The way we'll be able to determine if these gravitational waves are coming from binaries or coming from new fundamental physics is by mapping where the gravitational waves are coming from. Just like we can create maps of the night sky using electromagnetic radiation, we can now create maps of the sky using gravitational waves. As our sensitivity continues to improve, we expect to be able to detect whether the gravitational wave background is stronger on one part of the sky than another, whether there are more instruments from one part of the sky or another. We believe that this would be a definitive indicator that supermassive black hole binaries produce the gravitational wave background. If it is binaries, then as our sensitivity continues to improve over the next few years, we'll be able to resolve the structure of that gravitational wave sky and eventually be able to detect individual binaries that are loud enough to resound above the background. This would be a particularly exciting opportunity for multi-messenger astrophysics, in which both gravitational waves and electromagnetic signals can be observed from the same sources. Once this happens and we're able to see and hear these sources at the same time, we would be able to make unprecedented measurements about supermassive black holes and answer fundamental questions about where they come from, how they evolve, and how they interact with the galaxies that they live in. Next, one of our great founders, Dr. Maura McLaughlin, will tell you more about our collaboration.
Okay, well, I think we'll leave it there for today because very shortly we need to get reorganized for the next announcement today, which is about the ice cube neutrino detector at the South Pole. So obviously we would like to thank you very much, viewers, for being with us this afternoon. Sorry we had a bit of a problem in the chat there with an invader being a bit silly, but I've thrown him out and blocked him, so we won't be seeing him again. Anyway, thank you. If you do have any questions, now is the time to put them in the chat before we close for the afternoon. Or if you want to follow us over to our other live stream on our channel, we'll be going live in about, about 10 minutes, something like that. So you can ask the questions there if you like. If you look at our channel, you will see the other live stream for this afternoon listed in the upcoming events. So we hope to see you over there because, unlike the gravitational wave announcement, we don't know what this one's going to be at all. Just to recap then, astronomers have found, with the aid of pulsars, the background gravitational wave hum of the universe, if you like, that's coming from very, very low frequency gravitational waves originating from the mergers of supermassive black holes at the cores of galaxies throughout the history of the universe. And all of those collisions, all the gravitational waves in those collisions have come together to form this sort of background hum, stretching and distorting space-time quite loudly as it happens. So that's the headline for this afternoon. Of course, we're going to talk about this on next Monday's show. So if you like, you can ask any questions there that occur to you before then. Thank you very much for being with you. And if you would like to stick with us on the other stream, we'll be there shortly. And let's see what's been happening at the South Pole with the ice cube neutrino detector. Sounds intriguing. Hope to see you there. So from us, goodbye for the moment then. Say goodbye, Daz. Is your microphone? Your microphone's not working.
Okay then, sorry. Take care. See you soon.
Yeah, see you in a
Hope
bit.
to see you in the next show.
Bye.